So first of all, thanks for everybody's time. Before we start, I think a couple of high overarching comments, or maybe in order. Some of you, I see some of our friends here, but some of you may not know who Kove is. That may be changing here soon, but everyone in this room has used inventions that Kove has made, every single person. If you've ever used cloud storage, we invented distributed hash tables for location service. All scaling of cloud storage is done through inventions we made. If you have ever done any kind of a transfer of money, you have a bank account. The back end of that is the Swift network for transferring money. That's us behind that. That's about $5 trillion every day or two. It's the gross national product of all countries combined. 93% of all money in the world goes through that system, which goes through us. Now, before I get into the content, I'm going to say some things that are going to be possibly something you haven't heard before. And I want to invite everybody to think. Remember back when you thought what was really great about being in our industry is you could do something that really mattered, that inspired you to want to go into work or not go into work and be behind your keyboard and do the best stuff better. Like really. Remember that feeling, because we're going to start talking about some things that are interesting. I hope you'll find it. So anyhow. So unlike a lot of people, I think that the big challenge that we have is traditional DRAM. Everybody's saying, oh, we got to go to DRAM. The problem is we've conceptualized ourselves into a box where the way we see memory it's self-limiting. Now, this is the kind of classic picture that I think not a lot of people would find controversial. We know how to scale GPUs. We have big LLMs. They work. You can throw some brainiacs at a problem. You can have a bunch of servers, put a bunch of GPUs in the servers. You can figure out the segmentation of how you fit enough memory for each of the CEs, and you can scale it. Great. CPUs, we can do that too. You can virtualize CPUs. But memory, it's that stuff that's stuck in the box. And what do you do when you don't have enough? Well, you swap to disk or you use some other technology. That's the game. Now, that's not the way the world's working though. The world's wanting bigger and bigger models. They're wanting more reactive, more capable systems. Everybody's talking about memory. But as long as we continue to think about memory as stuck in the box, we are stuck in the box. Right? Literally stuck in the box. We build servers around the concepts of how it is that we can source enough memory in the box. Now, we were talking to, a very large global investment bank yesterday, and they said, yeah, we spend 60% of the cost of all servers is DRAM. And we target to use 50% of that in the best case and strand the rest of that deliberately, because what happens if you run out of memory? You go to disk, no problem, but that's 125 to 1,000 times slower than memory. Like this is de rigueur normal way of thinking. So it gets better, right? If you start adding racks and racks and racks. No, it gets worse. It's the same problem multiplied over and over and over. Now, why is it that we have to do that? Well, there are lots of reasons, and people say that, there's physics, there's the speed of light, distance of cable, there's cache coherency, and you can go through the list, and all the technical people in here can rattle that off because we've all tried to figure that out. Now, we've spent at Kove approaching 17 years on this one problem. Okay, we are in key distributions and global infrastructure around the world, and have spent on one problem. That's this problem. So what if, for real, not in a possible theoretical world, not in a maybe possible academic world, not in I'm going to create exception cases, exclusions, disclaimers, and then I'm going to make claims. But what if I could actually give you unlimited DRAM? What would that look like? Let's go back to this picture. So that's the way it is because the memory's in the box, right? Well, what if we could put memory right in the middle of everything because there's no limit, right? What if we were thinking instead of, how do I architect my systems around the limitations of what memory have? We architect our systems thinking, I now have as much memory as I need, when I need, how I need, where I need. What would that look like? Supposed to go. There we go. Well, this is what it might look like. This is what we do. So you can take some servers, and they have DRAM. We don't care what hardware it is. It's any hardware that is produced or supported by any manufacturer in the world that, as long as Linux works with it, it works. We have customers in production with memory that is 4 generations older than any memory you can buy today, working in supercomputing facilities at scale on the biggest scientific problems in the world. Now, what you would do is you would want any server never to worry about the amount of memory it has. It just raises its hand and it says, I need more memory, and it gets it. Now, what would that look like? So you'd have a pool of servers, let's say, sitting right over here. You'd have some servers sitting right over here. And whenever this server needed memory, you'd get an allocation on some composite relationship of that. And our software just makes it happen magically for free. And the application wouldn't be rewritten. I wouldn't have a disclaimer. I wouldn't have an exception. I wouldn't tell you that if you only did the following 9 things, it would work. You would hit buttons, and in 15 minutes, you could install our software. And that's actually legitimately true. It takes about 15 minutes to install the software. And then what do you get? Well, you would get this. Now, obviously, the next objection that the technical folks are going to say is, well, don't you know about physics? So a nanosecond, it can go about this far, okay, on a piece of copper, 7 inches, 12 inches in a vacuum. So if I'm going to put memory, let's say 100 feet away, what's the cost of that? I've just destroyed the computation. It can't work. Don't you know that? Yeah, that's right. That's the physics of it. There's also science. And there's also really good discipline science that says, yeah, I can address that. So what does that look like with us? This is what it looks like. We can hide latency 150 meters away. So remember this little example. I've got my little boxes over here. Think of it as a rack. I get my rack of systems, and I got some memory in there and targets. So but now I have systems, not racks. Okay, now 150 meters. That is on the other side of the building. Okay, I am including in this Rocky or InfiniBand plus a spine leaf configuration. So you get the 4.5 microseconds that you could pay on older equipment all the way up into, we're getting down a little less than a mic of overhead, plus the speed of distance, the speed of light distance of cable of 150 meters. Well, and does it work? How will it perform? Obviously, that can't perform as fast as the memory in the box. Remember, there's physics, right? We all know this. Every server manufacturer, every cloud provider, every nation-state government, every military will tell you you can't do it. Well, let's give you some numbers here. So everything here is an outcome, okay? These are not made-up numbers. And I'm going to show you something, going to give a little bit of teeth in a moment. That's 60x faster model training. Well, it's just because you're avoiding all of the glueware that you've got to do when you deal with storage or NVMe in box or whatever you want to do. If you're doing inference, let's say VLLM with Kove, and we can go 3 to 5 times faster. I'm going to show you some results on KV cache compared to local DRAM. Now, that'll be the next. 100x container density. I think I saw a colleague from Red Hat somewhere here who did some of this work. If you can apply the right memory at the right time and the right place, 150 meters away plus a spine and leaf organization, I can still give you 100x performance improvement or scaling factor of containers. Memory. If you control the memory surface, you control a whole lot more than people are realizing. Power. So What are you using a lot of power for if you're not using stuff? Now, the chip manufacturer is very clever. They will power down the DIMMs that are not being actively used, but you're still having big systems where you have stranded memory, which are running, guess what? Processors. And processors are the things that drive the heat and the power. Well, if I can change that game, I can use fewer processors more efficiently at the same heat and power output as I could more running less efficiently, observing and needing more power. So again, there's somebody in here who did the study. Supermicro, the CTO's office of Supermicro and Red Hat did a 3-month study on our software and concluded that you can save 12 to 54% power reduction by using Kove software on any hardware that Linux supplies. No code changes, no rewrites, no exception cases and disclaimers. You plug it in, you hit buttons, and it goes whir. Okay. Well, next objection. Well, my gosh, I'm going to improve. I'm going to make the blast radius terrible. And, this is going to destroy my cloud. I can't do that. Okay. The full recovery time, if you have an allocation that fails and it comes back, it can be about 200 milliseconds. So just to be a little bit obnoxious, that's literally how long it takes you to blink your eye. Okay. So one option is you can take the server offline. You can have somebody show up for 4 hours and fix it. The other is you blink your eye and you get new memory. The 6X on CPU is trivial, easy to do. Okay. I want to start talking some numbers because the proof is always in the pudding. So Red Hat is one of our partners, and in the case of they're doing VLLM, so we did some testing on some KV cache. How would it work? So we tested Redis and Valkey. Reason we tested Redis and Valkey is, because that's what everybody uses. It's not really, we don't care so much. Now, I want to really set the stage because I'm going to show some performance facts. Let's imagine and just remember what Redis and Valkey do. It's a single-threaded application that does a DMA 2 inches across the motherboard on a local server and does a hash lookup. It's very hard to make that a more reduced impact computation. So now remember, I'm going to put memory 150 meters away. So how's it going to go? Well, we're obviously going to get destroyed. I've taken the worst nightmare that could ever be approached to Kove. I have a fully randomized hash table. I've got a 2-inch DMA lookup and it's single threaded. And I'm going to stick something with switch hops, a football field and a half farther away. So what I'm going to show you right now are some benchmarks, first with Redis and then Valkey. In the case with Redis, everything you're going to see on the page was run 7 times in average. So the first test is you run in local memory where there is literally no Kove. It is bare metal. There is no anything we are related to. Okay. I can't say that loudly enough. Then we're going to add a multiplier of a larger amount of memory. We're going to then run that same benchmark or series of benchmarks, and I'll show you which one it is, 7 times an average. So we even run at 7 at HPC. That's a kind of classical, you do it to eliminate experimental skew. We're going to run that 7 times, and then we're going to compare the delta between us over yonder and a DMA, right? This should be about as bad of a scenario as we could ever imagine. And we're going to do that over a bunch. Now, these benchmarks that we're going to show you, you can run it on your own systems. They've been duplicated all over the world. There's no way you can refute these results. They are as legitimate and hardcore. I think when you run the full benchmark, it's 50 pages of data and so forth. We're only going to give you the summary, the heat map, and say, how do we do compared to local memory? Now, for all the technical folks in here, I want you to imagine just for a moment, put it in your own head. How bad should it be for us? 150 meters cable, switch hops versus a DMA. Here are the answers. For Redis, on that, you can now do more things with Redis than you ever imagined. Okay? You see all that green? What does that green mean? Well, this is the Redis Benchmark 724 run on an Intel Xeon at Oracle Cloud Infrastructure. I don't know what the distance is. I don't care. Okay? That's the kernel. and it was running rocky. At the 50th percentile, the median, Kove is 11% faster than local memory at 5 times larger. For gets, we're 42% faster than a local DMA. In the other building, 5 times. Now, let this hit the brain, what you might do. This is provisionable memory. Remember, the simplistic view of this is I've got some servers here that are targets, and I got some server here that are consumers, and all I'm doing is matching up what I need. All that stranding that I mentioned about that bank, yeah, we buy 60% of the cost, and 50% of that we strand on purpose because we can't afford not to. Poof, it's gone. Okay, now maybe we were lucky, and this is the Redis benchmark. So Valkey is the other it's a branch out of Redis with separate development infrastructure and so forth. So we ran the same thing on that, again, on the Oracle Cloud Infrastructure. How did we do on that? Same kind of thing. A lot of green. Well, darn it. We're only 10% faster than local memory. 5 times larger, 10% faster. And on the gets, we're only, 1% faster than a local DMA. Okay? So if you are a cloud provider, I just am demonstrating for inference a 5-to-1 reduction in hardware for the same result. Oh, I'm sorry, it's faster. Okay? Or I can do 5 times more work. Oh, there's obviously a whole lot of extra stuff you've got to do. It's called hitting a button, installing our software in 15 minutes, and then applying provisioning rules that take about 30 minutes. And in 2 weeks, you can duplicate this for anything that you do in your infrastructure. That's it. Oh, and it works on any device in the world. And right now, you're already kind of using it if you do stuff or you don't know it. Okay. So let's talk some numbers here. So one of our partners, I'll mention those in a bit. This is a deal that we're doing for hospitality. And this is the kind of savings that you would get for a good-sized enterprise. Okay, this is more for the business folks. 8 to 10 IT savings, 5 to 15 on better availability, better function, and 20 or so in productivity. Now, let's imagine that I'm a data center provider. How many enterprise customers do you have? I'm a cloud. How many enterprise customers do you have? These numbers are the small numbers that are the unambiguous, very, very, very difficult to refute numbers. They're actually a little bit bigger than this, but we're being more conservative. So this isn't just coming up here and being a geek and saying, look at how cool. Ma, look at me. I'm riding my bike with no hands. Right? This is fundamental business that leads to fundamental outcomes. And it is only software. Okay. So if you're doing inference right now, and people would say that in inference, that's where you're going to make money, right? And the trick about inference is it doesn't have the same structural predictability that you have with the big LLMs. I can throw resources to create a big box, but still a box. But in inference, I submit a query, or a user submits a query, and then it goes in and hits a model, and the model passes to another model, and that passes to another model. There's a whole bunch of stuff that's going on behind the scenes, and then they build some stuff up, and then they feed it back to you, and they capture the state, and then you do it again and again and again. That's the way you make money. Okay, remember the bank, 60% of the cost of the server is memory, 50% utilized in the best case, 50% stranded. I throw it away on purpose. Now I'm going to do inference. Now, the last thing I ever want to do in inference is I want to be hitting the GPUs for the stupid, silly stuff that's repetitive, right? They should be doing the stuff that GPUs do, calculating real calculations, not spitting back caches, right? Well, we can just tier it and go to storage, right? Storage is only 100 to 1,000 times slower than you have DRAM. So that's my scaling factor to make inference profitable. I'm going to do all of that. What if I could just use memory and I could make it completely transparent and automatic? Go back and remember what it was like when we got into the industry. What if I could build the best still better. That's what you could do. Okay, but it's not just the KV cache. I'm using that because that's an unambiguous one that everyone's talking about. But there's really kind of no limit. It's the memory surface. So let's talk some numbers here. So Swift, I mentioned before, there's one of the companies that we can talk about that we work with. So that 17-hour job, they installed OpenShift plus Kove. They reran the job. And it took 4 minutes. They didn't believe it, right? You mean I hit a button and did this? I didn't architect it. I didn't change my application. I didn't do anything. I just hit a button. So they took the hardware. They shipped it to another part of the world. They gave it to an entirely separate team. Didn't say anything about what it was, but run this model, okay, on this hardware and see what happens. By the way, I don't even know what the hardware was. I don't care. We're software. Same result. Let's think about other areas that you could do. What about vector searches, right? This is a magic goodness. What are the things that you might do with a vector search? Well, I could know my customer, way better. I could have billion scale embeddings. I could do all of that in memory so I don't have that SSD issue. I mean, you're still welcome to use SSDs. We're equal opportunity capitalists. We love everybody. There's lots of smart people doing lots of smart things. Don't get rid of your storage. Don't get rid of your GPUs. Don't get rid of your servers. Just be better at being best. Be smarter about it. Okay, what if, let's say I was in big pharma and I could increase my toxicity analysis by 3 orders of magnitude because I could run it in memory. This is a configuration choice. It's a design choice. That's it. Okay. What about streaming analytics? So the standard de rigueur is you build your servers to the peak stamp because it's the best way to do it, the most economical, the best way to manage your infrastructure costs. What if you had all of a sudden infrastructural memory that worked on any piece of hardware that you had at all? New game. Well, what would you could do? What would you imagine about sliding windows that you might want to think about? Well, you could do population scale things that you never imagined. Let's pick health just for example. Let's imagine that I'm going to do some kind of an analysis for nations, then states, then cities, municipalities, down to cars or communities, biometrics that you're wearing, oxygen sensors in your car. I then could correlate all of those simultaneously, if I need to, using sliding scales. Imagine drone swarms for military. What if I could do all of that in real time where I am selecting for the size, shape, velocity, the perceived density, the possibility of payload on which of those? I have 1 million drones going in there. You can't go and take guns and shoot at them. You have to use tech. And you have to compute it. And you have to do it in real time with automated mesh networks. The only way you fight that is memory. And the only way you do that is to be able to use memory flexibly. Okay. Let's imagine some other scenarios where I just want to, I'm not even necessarily getting fancy schmancy about my modeling. Let's imagine this scenario. I just want to do things better and faster. So let's say that I have a particle accelerator and I want to capture 1 million frames in a second because I'm looking for subatomic particles. Okay. So what do you do with that? I'm just going to throw a huge game of SSDs at that. What's the latency of an SSD? I said 1 million frames a second. Okay. You can do things you never even imagined. Because all of a sudden, memory is this new friend. Put memory in the middle of the game. Not at the bottom, not fixed in a box. Use our brains and let's think about what could be done if we go another direction altogether about how memory can be. So look at this. Oh, HBM, that's the solution. No, it's memory. So you put HBM on the GPU. It's fantastic. Great. And then you have DRAM, then you have your SSDs, and you go through that little chain if you want to do that. Great if you want to do that. But if you had arbitrarily scaled memory, Would you do it the same way? I think you'd keep the HBM, and I think you'd keep storage, but you would think differently. That's what I was starting to invite you to think about. What if you could go back in your career and say, gosh, it's exciting. It's exciting to be alive and to be able to do things for the first time. That's what we're offering right now, the world, and for you to consider. Okay. So going back to the original part of my conversation, I'm going to have to hop here in a second, but going back to my original conversation, why wait? We have partners. So if you like, depending on how you like to work with us, you can come to us. We love to talk to people. If you're a cloud provider, you're a data center provider, you're an enterprise, come talk to us. Okay. If you would prefer, you can use KPMG. You can use Accenture. Sanmina, I think, is here. They sell $10 billion, a year. They build a memory tower. You can roll in memory towers and get the same functionality at that. Red Hat's here. Come to the Red Hat booth. If you would like to talk more, we'll have some people huddling. I'll be around here if you'd like to talk a little bit more. What I'll close with is, this is not theoretical. This is not in some possible world, in some possible universe. Wouldn't it be cool? It's deployed, and you actually are using the benefits or the inventions that we have been making for over a decade right now. Come talk to us. Let's go build the best stuff ever. Thank you very much.